Alrighty, so today we're going to be looking at Vox-Fusion, dense tracking and mapping with voxel-based neural implicit representation. This is a paper coming out of Zhejiang University, and more importantly, SenseTime, which is a computer vision company in China that has huge government contracts for pedestrian monitoring and kind of has a ton of expertise. So definitely a heavy hitter, maybe not in the Western sphere, but in the Asian sphere for sure. This is also, let's close out of this, very recent, just a couple days ago. Cool. So this paper, I kind of picked it out from Papers with Code, of course, and I like it because it seems to use a bunch of different things, right? So once we go through it, they present a dense tracking and mapping system called Vox-Fusion, which fuses neural implicit representations with traditional volumetric fusion methods. So neural implicit representations are kind of these nerfs that you've been seeing around, where rather than kind of explicitly saving objects as meshes and textures, people are now storing scenes as neural networks, right? So within the embeddings of a neural network is the content of the scene, and then given a new camera angle, you can basically render the scene as you would see it from that camera angle. So they do this, but they actually kind of put it under a SLAM kind of framework using voxels and kind of storing it in octrees, so it's efficient. And I think that this is an interesting kind of combination of a bunch of ideas that have been floating around. These are the voxel grid. So in this image, right, each of these little squares traced out in black is a voxel. Fuse. So inside each voxel, they fuse the color and depth observations into a local feature embeddings through volume rendering. All right, so that's the nerf component of it. So basically, inside of each of these little boxes, there is a nerf. Yeah, specifically, we leverage a voxel-based neural implicit surface representation to encode and optimize the scene width inside each model. Furthermore, we adopt an octree-based structure to divide the scene and support dynamic expansion. Yeah, so dynamic expansion. Octrees, I think they'll explain it later, but octrees are basically a way of partitioning 3D space. Yeah, here's a octree structure. So within the kind of a bigger square, right, this big blue square here, you can divide it into, on each side, 4, right? But if you do that, if you take a square or a cube and you cut it in half horizontally and vertically, you're going to end up with 8 cubes inside of it, right? And that's the root of the word oct, is octo, like 8, octree. So within each voxel, within each cube, there are 4 subcubes, which each partition the space in, I guess, 1/8, right? And this allows you to kind of create this tree structure where you can basically store information in a very kind of efficient way. By, if you need more and more resolution, you can just keep dividing the little subsquares. They're each little subvoxel, and you can have what are called, for example, empty nodes. So if there's nothing in a particular voxel, you can just leave it empty. So this has been around for a while. This is also a classic computer vision interview question, but using it with neural representations I haven't really seen before. So I'm curious to see how they make it work. Okay, our Vox-Fusion can be used in augmented and virtual reality applications. That actually sounds super cool. Okay. Yeah, simultaneous localization and mapping, SLAM. This is a classic problem of moving through an environment and both mapping the environment and localizing yourself in that environment at the same time, right? So building a map and positioning yourself within that map at the same time. So the 6DOF poses, right? 6 degrees of freedom. You have the 3 degrees of linear position. You want to say that? Cartesian maybe is a better word. X, Y, and Z. And then you have 3 degrees of freedom to represent your rotation of a moving RGB camera whilst constructing a dense map. Okay. Essential part of AR and VR. Yeah, there's a ton of different ways to do SLAM, right? And there's a lot of people were doing this way before deep learning. So there's a lot of classic ways of doing SLAM, and kind of over the course of the deep learning revolution, different parts of it became learning based, and yeah, it's kind of a huge mishmash. So here they have a ton of different references here. Yeah, they are incapable of rendering novel views and cannot hallucinate unseen parts of the scene. So that's kind of where the neural representations would come in useful there. Yeah, storing and distributing the maps takes a ton of VRAM. Okay, so they say there's some recent works, such as CodeSlam, that can encode the depth maps, right? And that allows you to, usually these, a neural network with kind of a very small embedding space will be cheaper from a memory perspective, which is allows you to kind of trade off memory usage here, scene quality memory usage. Okay, however, the pre-trained networks using these systems generalize poorly to different types of scenes. Consistent global representation. Okay, some issues with that. Okay, so here's some recent works that do dense SLAM with nerfs. Yep. Here we have IMAP using a single multi-layer perceptron, right? Just a multi-layer neural network to approximate a global scene map and jointly optimizes the map and the camera poses. Okay, here they're saying that using a single MLP for the global map makes it harder to scale to larger environments that maybe have a little bit more diversity in what's inside of them. Yeah. So this is really the meat here, right? Sparse voxel representation with neural embeddings. Okay, so maybe a little bit more information here on the octree. It's a sparse octree with Morton coding for fast allocation and retrieval of voxels. What the hell is Morton coding? Morton encoding. A Morton order is a mapping of n-dimensional space into a linear list of numbers. If you apply it to coordinates, the Morton order defines a space-filling curve which is z-shaped. Z-order or z-curve. Okay, so I guess here you have a picture of a cube, right, which could represent a voxel, and how do you encode this in an efficient way? And it basically seems like this particular pattern, right, like ordering these corners in here they're calling it a Z, right? So you go from 0 to 1 to 2 to 3 to 4 to 5 to 6 to 7, and that somehow makes things faster. Okay, so you're interleaving the bits. So let's say you had XYZ coordinates of 5, 9, and 1. This is the binary representation of each of those numbers, and then you interleave those bits. Okay, kind of cool. So they're doing some tricky stuff with the octree here. We modeled the scene geometry within local voxels as a continuous sign distance function. That's fine. That's what all the other nerfs do, which is encoded by a neural implicit decoder and shared feature embeddings. Tracking and mapping. Okay, so it's the combination of this voxel embeddings and the neural implicit networks. Directly rendering sign distance volume provides better tracking accuracy and reconstruction quality. Okay. I mean, number 2 here is hard to prove, right? Like, especially with kind of the market of autonomous vehicles and robotics, a lot of this stuff isn't necessarily published anymore. So, like, what is the current state of the art in SLAM? It's very difficult to say. There's no benchmarks. Different companies are using their own internal tests to benchmark their things, right? Like, how good is Tesla's SLAM? What does SLAM even mean in the context of a Tesla car, and how would you compare that to this SLAM? So, I don't know. I think number 2 is kind of a moot point. They're just going to probably introduce some benchmark that they beat. We propose to use a fast and efficient keyframe selection strategy based on ratio test and measuring information gain, which is more suitable to maintain large size maps. Okay. So keyframe selection, what does that mean? So, right, you have a video. So you're moving through this little scene. That's what this green line is basically the center of the camera, right? And this is probably a cell phone, right? This looks like the inside of some guy's room. So you have to pick which images, right? You have all these images coming in. You have to pick which ones you want to use to create your map and to localize yourself within that map. So picking the right keyframes to do that is important. And so I think they're going to measure information gain here and then do some kind of ratio test to determine which ones to use and which ones not to use. Perform extensive experiments. Okay. Demonstrate the proposed method is producing high quality. Okay, so they have three parts. They have one, the volume renderer, encodes the scene in an MLP and embedding vectors and outputs the rendered color and SDF value for a given pixel. Okay. So this is the nerf. Tracking process, number 2, which takes as input RGBD frames and optimizes the camera poses via differentiable renderings. Okay, so you're tracking, takes the image and then given kind of the map determines where the camera is. And 3, mapping process, which reconstructs the geometry of the scene. So this is the localization part, number 2 of SLAM. 3 is the mapping, so the M part of SLAM. And then you have 1 volume renderer, which is also part of the mapping part, I would suppose, I guess. Okay. So I'm sure we'll go back to this image a couple times, but we have the RGBD stream, right? Red, green, blue, and depth. This is otherwise known as a 4D camera sometimes. Having an explicit depth stream like this usually means you have some kind of, it's not just a normal camera, right? Either it has some kind of structured light depth sensor or time of flight or something. Maybe, I think the most recent iPhones have these type of sensors on them too. So it's one of those. So they take these frames, sample rays. So when you create nerfs, you have to know the direction of the, or you have to know where the camera is, and then also where each of the rays that come out of the camera are. So that's probably what the ray sampling here means, is they're picking specific rays within that camera pose. Volume rendering, and then pose update. So there's some kind of feedback loop going on here. This is the tracking process. So I think this is the takes as input RGBD and optimizes the camera poses via differentiable rendering. So maybe what it does is it basically takes the pictures, determines where the rays would go, uses that to render based on the current map, and then says, okay, well, how close is what I just rendered to what I'm actually looking at right now? Volume rendering, which is this little orange box here, is expanded here in this box. This is your standard kind of nerf formulation where you have a camera in a position, it projects a ray on points along that ray, which you sample, right? Points along the ray, and the ray, you feed that into a little multi-layer perceptron, and it'll output, and it'll give you the color, and S, which is probably the sign distance function, which is basically just the depth. Cool. And then finally, the mapping process. You have some initialization for the map. You create these keyframes. You voxelize the scene, right? You break it down into these little voxels. This is kind of where the octree comes in. And then there's this repeated process of selecting keyframes, right? Selecting individual pictures and individual RGBD pictures from the stream, individual frames from that video, sampling the rays, rendering the volume, and then going back and comparing them. So this process here, the take a keyframe selection, which is basically image into ray sampling into volume rendering into pose, and then going back to comparing that to the original images. That happens here, and it also happens here. So that's kind of the meat of this process. DTAM introduced the first dense SLAM system that uses every pixel photometric consistency to track a handheld camera. So I wonder what this paper is. Citation 20. They're telling us that the first dense slam happened in 2011. I don't know about that. I would say there's probably an earlier reference than that. But I don't know. They employ multi-view stereo constraints to update a dense scene model. Connect Fusion. This is again another type of older work too, but this is with the OG Microsoft Kinect, which used to come with their Xboxes, and then eventually I think they started selling it as an individual sensor because a lot of people were using it for not just the Xbox, and a lot of sensors are kind of based on this technology, which projects infrared kind of patterns and then uses an infrared camera to measure the distortion on those patterns. Commodity depth sensors. Iterative closest point. This is a very old computer vision strategy for aligning things. Okay, they kind of reference some of the earlier works where people are using the latent spaces of the low-dimensional latent spaces of neural nets. Here they say that the geometric prior is inaccurate for complex scenes. Encoder decoder, so this is probably kind of around the timeline of VAEs, and this whenever that kind of craze took over. It seems like the kind of main negative about the older learning-based approaches is kind of the lack of robustness to scene variations. I would say that maybe part of that is just that they were working with probably shitty data sets that were limited to a specific domain. But I don't know. Water under the bridge, right? Recent concurrent work proposes to tackle by subdividing the world coordinate system into uniform grids. Okay. That's what a voxel is. Yeah, so right, even though octrees are an efficient way to kind of break up 3D space into a bunch of little squares, I think that they say here that basically the dynamic allocation of voxels is important, right? So if you look at kind of their crowning image here, right, it's not like they took a 10 meter by 10 meter by 10 meter square and started with that as the initialization for the entire map and then just subdivided that entire thing into tiny little voxels. They seemingly kind of add more voxels over time, right? So like this dynamic allocation of voxels is something that they say is going to improve, reduces memory consumption. We'll see exactly what they're doing. Okay, little Nerf paper reference here. Yeah, so this is something interesting, right? Where like Nerfs, they're very good for transparent images, but you need, for most AR tasks, it is important to know where the surface lies. Right? So if you're setting something down on a table, right, you kind of want to know exactly where the surface of that table is, right, so that you can actually set virtual objects down on that. But these nerfs, right, a lot of them don't have that, right? It's kind of you have a ray that's coming out of the camera, and then you just have colors along that line, and then you have kind of density, usually opacity sometimes it's called, at those points. And you might end up having like 4 points that are all within maybe a couple centimeters of each other that are all kind of darker opacity, and whenever you look at that, render that nerf from a novel camera angle, it kind of looks like there's a surface there, but in reality there's no explicit like kind of mesh. There's no explicit position for that surface. Yeah, so sometimes people kind of force the ray sampling to kind of get more details as you kind of, if you have a point along the camera ray that shoots out that has a high opacity, then you kind of sample more around that, and that allows you to kind of learn more about the details on the surface. Okay, a couple other papers here, NSVF and planoxels. And then NG-LOD. Okay, here's some other works that use this kind of voxel-based nerfs. Yeah, I think this is kind of maybe low-key the most impressive part of this, is that in pretty much all of these nerf papers, right, in order to construct the nerf, you're doing supervised learning, right? You have a bunch of images of an object, and the camera pose for each of those images is known, and then you're effectively teaching or training this little multi-layer perceptron here, right? You're training it on the pairs of, hey, at this camera angle with this ray, this pixel should be this color, right? But in this paper, they're not doing that. They don't require posed images, and it's an online system, right? It's running in real time and simultaneously creating the map while localizing itself in that map, which is, I think, a lot harder, right? Rather than taking a bunch of already existing pictures that have poses associated with them and then just building a kind of nerf from that. Yeah, and then really the dynamic growth of the map is pretty cool too. Okay, this is actually the Morton coding that we were looking at. So it's this idea of kind of having a specific pattern that you kind of like go through each of the voxels in the space such that you can interleave the bits, and then somehow that's more memory efficient. I don't know. I wish I was cool enough to really deeply understand why it's better. But hey, maybe they explain it in a way, this paper, that makes it easier to understand. Input to our system is a continuous RGBD frames. Right, you have RGB images, which three-dimensional, and then you have depth maps, DI. So I for image, and then DI for depth, and I'm assuming I is going to be the number of frames in a sequence. We use a pinhole model as the default camera model, so you're going to have a focal length and a camera plane and all these kind of standard things from your computer vision geometry. Zoom, okay, you have intrinsic matrix, camera intrinsics. Similar to other well-known SLAM, maintain two separate processes. Yeah, so you have kind of both. You have kind of a tracking process which maybe runs on the actual edge compute of the cell phone or the robot, and then you have the kind of map creation which is happening in a back end. This separation is really popular in robotics too, for kind of it makes the computation easier to separate, right? Where the actual robot is going to have a smaller compute footprint, so you're going to task it maybe with just one part of that, or maybe even just 0 parts of that. Maybe it just takes the images and then just sends it to the backend. But usually the creation of the global map and the optimization process around that can be very heavy, and it might be useful to fuse the kind of input stream from a variety of robots. So in a multi-robot context, it even makes more sense. So yeah, they're separating it here as well. We initialize a global map by running a few mapping iterations for the first frame. Okay. Okay, so we have a 66 DOF pose, TI, which is SE3, which is Special Euclidean Group 3, which basically just means X. Let me see the official definition of Special Euclidean Group SE3. So this is, group is a math construct. It's a definition of kind of things that have specific symmetries and properties and so on. But specifically we want SE3. I think it's translational. No. Special Euclidean Group 3. SE3. Here we go. SE3. You have R, which is the position. You have big R, which is the rotation matrix. Right, rotation matrix big R has 3x3 elements. Right, it's a rotation matrix. Little r, which is the position, has 3 x, y, z. This is saying that if you the transpose of the rotation matrix times the rotation matrix is equal to the rotation matrix times the transpose. So inverting the rotation and then rotating is the same as rotating and then inverting the rotation, and those are both the identity. And then the kind of magnitude, or I guess the matrix, rotation matrix itself. Okay. Cool. Right, this would be, for example, this is a 2D version, so this would be the x position of the robot, y position of the robot, and then this part right here, cosine, negative sine, cosine is the rotation matrix. So let's go back to the paper. So 6 DOF pose in SE3. fixed implicit scene network. It's not going to be fixed always, so let's just say implicit scene network f of theta. That's going to be your nerve, well, the neural part of the nerve. Takes the estimated camera poses ti from front end and allocates new voxels from the back projected transform point cloud. Okay, where did that come from? Now suddenly we have a point cloud? Okay. We only maintain a small number of keyframes which are selected by measuring the ratio of observed voxels. Okay, we'll see what that actually means. Okay, an implicit sign distance function decoder f theta. Okay, which has some parameters theta and a collection of n-dimensional sparse voxel embeddings. Okay, the voxel embeddings are attached to the vertices of each voxel and shared by neighboring voxels. Okay, so that's actually probably why they're using this Morton encoding. So each kind of corner of the voxel allows you to share the embedding between all the neighboring voxels. Yeah, and this alleviates border artifacts. It's kind of a cool thing. Okay, for each sampled pixel, so whenever you take a estimated camera position and then you project a ray from that and it crosses the camera plane, and that tells you that in a sense is what the pixel should be. They first do is they check if it has hit any voxel along the visual ray by performing a fast ray voxel intersection test. So let's go back up here. Their camera is here, right, and it's going to project a ray. That ray is going to travel through the scene, and you can very quickly, right, just using kind of geometry and triangles, calculate which voxels are intersected by that ray. And this is a way that they save computational power by not having to sample spaces that aren't actually connected by that ray or touched by that ray. Okay, so there's a limit on how many voxels a single pixel is able to see. Okay, they dynamically changed this limit based on the maximum sampling distance Dmax. Like NERF, where the MLP is used to predict occupancy. Use voxel embeddings instead of 3D coordinates. Yeah, I wonder how they're sampling those points along the array, because that's usually where there's a lot of tricky custom stuff in different nerf works. Okay, so this is the neural network. They're giving it a tri-lerp here. Tri-lerp is the trilinear interpolation function, which itself is receiving EI, TI, PI. So E is the frame pose, so the pose of the camera. TI, we saw earlier, is the estimated camera pose. And PI, maybe the point cloud, so the individual point. And then what is E? Voxel embeddings E. Okay, so the color CI and SI, the sign distance value function, which is effectively just kind of the depth, if you want to think of it that way, is you get it from feeding a bunch of these points, modifying them based on the transformation of the frame and the camera. But you're also interpolating in. Normally, when you have a this neural network, you're feeding it the position of that ray. I think here what they're trying to do is they're feeding it also the embedding of the voxel. And not just the embedding of the voxel embedding, but the interpolated voxel embedding. I don't know if like that type of interpolation messes with the embedding space. Sigma is the sigmoid function, right? So sigmoid is basically it caps it. So people use this as a nonlinear layer inside neural networks, and basically it caps, given an input of infinite magnitude, right? It could be negative infinity or infinity. It'll cap it between 0 and 1. So TR, SI over TR, negative SI over TR. And that gives you whatever WI is. What is WI? Oh, WI might be the weights. Oh, okay. So I think all they're saying here is that this is their MLP, and they're just saying at the very end of their MLP, we have a sigmoid that makes sure that our color and our depth, all of the weights, depth is all of the weights as well. So the color and the depth share the same weights. What is D sub j? TR is a predefined truncation distance. Okay, that's this term here. Weighting sample distance. Okay, so I think these WIs are the weights. Of the distance. Okay, all right, this makes more sense now. So we have our neural network here, right, which is outputting our color and the signed distance function. Then we're going to take this signed distance function, we're going to divide it by a truncation distance, and then we're going to have the negative version of that distance function over the truncation distance. We're going to put those through a sigmoid, multiply them. That's going to be our weight. And that weight is going to be multiplied by all the little individual colors that you get, right, in capital N, which I guess is the length of the video, or endpoints, right? So all the points along the ray that you sample, you're going to weigh each of those based on the signed distance function. Right, so if we think about how would we get a very large value for the weight? A very large value for the weight would have, assuming TR is the same, right? We want very large positive numbers in order to get 1. So a very large positive number means that SI is big. I mean, I don't know what this dot product here means, right? If you have 1.0 times 0.00001, is it better than 0.5 times 0.5? Difficult to say. Okay, but either way, this is how you get the color and the depth for each ray, which basically means for each pixel at a given camera pose. Okay, so to supervise the network, they have 4 different loss functions here. They have RGB loss, depth loss, free space loss, and SDF loss. On the sampled points P, these are, so there's points that you sample along the ray, and then I think there's just points in their point cloud. Yeah, 3D point cloud, PI. RGB and depth losses are absolute difference between the render and ground truth images. Okay, so you have the color at this point in the point cloud, and this is the ground truth color, and you're subtracting from the color that you get out of the nerf, and same thing with the depth. You're just subtracting those. It's an L1 loss, and you're averaging it over all the points. I feel like it probably would have been worth to, we'll see how they combine these loss functions, but I think the depth might be more important than the color. The ith pixel. The free space loss works with a truncation distance TR within which the surface is defined. Okay, this is the depth, D. This is the truncation value, truncation distance. For all points S in SP f of S, okay, then they have an SDF loss here. Okay, so they're saying if the truncation value is negative behind the truncation region, we simply mask out these points during rendering to avoid solving surface intersection ambiguities. Is there a good image of this? Sorry, that was probably kind of gross. During tracking, we keep our voxel embeddings and the parameters of the implicit network fixed. Okay. So when they're tracking, the nerf, which is this f theta here, are fixed, and they're using that. And then I guess the mapping process will update those. So there's this kind of like iteratively updating the network and then using that network to get the current camera position. And I'd be curious to see kind of how fast those alternate, like how long those goes. Like there's all kinds of interesting questions there where you could start trading off like the cost of updating the map, maybe how many times per second you need to update the map, how many times per second you can do it, like the measuring drift. Like there's a lot of hyperparameters and trade-offs there. Suppose update in the tangential space of we assume a zero motion model where the new frame is sufficiently close to the last tracked frame. Therefore, we initialize the pose of the new frame to be identical to that of the last tracked frame. That kind of seems wrong, right? Okay, for each frame, we sample a sparse set of NT pixels from the input images for tracking. Ooh. Actually, what would have been cool is instead of just randomly sampling pixels from the input images, like imagine if they would have used like some kind of sift, or maybe not sift or orb, or one of these old school key point detection models, but like maybe a more modern one, right? I think it'd be more useful if the pixels they used for tracking were like the corners of tables and stuff like that. Okay. Okay, so the map copy is directly obtained from the mapping process and updated each time a new frame has been fused into the map. So, okay, so every time we get a new frame, we update the map. And here they're going to tell you how often they do that. Right? Is it a fixed interval or some kind of metric? Our explicit voxel structure allows us to determine when to insert keyframes by performing an intersection test. Each successfully tracked frame is tested against the existing map to find the number of voxels that would be allocated if we are to choose a new keyframe. Okay. Yeah. So this is kind of a goal strategy where they take a frame and then they look at that frame and then the current map, and they look to see which rays coming out of that frame, which voxels does it intersect, right? NC, right? Where each ray is coming from a sample of NT pixels from that frame. And they say how many of these voxels, NC, are there compared to the number of voxels that are currently observed. I don't know if that means in the overall map or just like in the frame beforehand. And then there's going to be some ratio there, and then you basically have a hyperparameter, which is the ratio of kind of the new frame, the number of voxels that this new frame is going to intersect versus the number of voxels that you have total. Yeah, I guess this is true. This makes a good point, right? So if you're in a situation where you're constantly moving the camera into new space, this is great, right? Because it basically automatically starts adding to the map, because each voxel that you're seeing is a new voxel, right? You're like exploring new parts of the space. But let's say instead you had a different type of scene, right? You had a scene where they call it loopy, but basically you have a camera just kind of moving around in the same place over and over again, and then the stuff in the actual place keeps changing, right? Maybe you're looking at, I don't know why you would perform slam where all you're doing is just staring at a single dog, for example, or something, or like an animal that changes. But yeah, you could be basically always, you could get to a point where you never allocate new keyframes, never kind of re-update the global model, because as far as your system is concerned, you're not really moving, you're not intersecting any new voxels, therefore the ratio, this tuned ratio, is always going to prevent you from adding new frames to the map. Okay, so to do that, they enforce a maximum interval between frames. So if you haven't created a frame in some amount of frames, you will automatically create a frame. Yep. So it's just jointly optimizing the frame and the already existing ones. Okay, so online incremental learning. So what they're saying here is that if you have a network such as the one here that is being used to render the color and the sine distance function, right, our NeRF network, if you are constantly pushing gradients to that, over time, right, the gradients that you pushed in the beginning are going to kind of disappear, right? It's like you might as well have never have done that, because you're now you've kind of moved away from that, right? And sometimes that's called catastrophic forgetting, right? Where you'll take a classifier, for example, train it to differentiate between cats and dogs, and it works great. And then you take that same classifier and then you start training it to classify between cars and airplanes, and it'll forget, right? The weights that were useful for classifying between cats and dogs will kind of get overwritten over time. So what they're saying here is that in order to prevent this forgetting, which in this case basically means that the NeRF is good at representing earlier parts of the scene versus later parts of the scene, earlier and later being in time, right? So stuff that you keyframes from the beginning of your session and keyframes from the end of your session. So in order to solve that, they're going to jointly optimize the network and the embeddings, and they're going to select some random number of keyframes, or some random keyframes, which includes the most recent frame, and They're comparing this to kind of a sliding window approach. Okay, and then for each frame in the actively sampled optimization window, we randomly sample in range. So frames, think of them as images. RGBD are actually 4 images or 4-dimensional images. And then from that, they sample rays, right? Which are kind of like individual pixels, individual rays coming out of that pinhole camera model. Those rays are transformed into the world coordinate system because you have an estimated position of that camera. And then you sample points within the sparse voxels based on those rays. And then once, right, you sample the points in the voxels based on those rays, and then those get you the pixels, and then those are the pixels that you use for the loss functions. Axis aligned voxels. What does that mean? That just means that there's kind of this prior that they're using where the 3 dimensions of space x, y, and z, right? There's an z going up and x and y. So that's kind of the axis aligned, right? The voxelization of the space assumes a rotation, right? Example octree is shown in figure 4. I think that's the figure we were looking at here. Yep, this is the Vox tree showing kind of empty nodes, leaf nodes, which is where information actually sits. Right, you have this little dragon here. Black are voxels that contain actual stuff. Those are black. These X's are the empty nodes, and then the red boxes and green boxes are kind of coarser representations of, or coarser partitions of this 3D space. But the actual information, such as the color or the sign distance function, will be stored in the finest resolution here, the leaf node. Okay, leaf nodes are empty. We back project the depth map into 3D points, so that's kind of how they're getting the point cloud that they were talking about earlier. They're using the depth, which is coming from the sign distance function, and since they know the estimated position of the camera, right, then you can get a 3D point in the world space. We allocate new voxels for any point that does not fall into an existing voxel. Morton codes are generated by interleaving the bits from each coordinate into a unique number. Okay, so we were talking about what the fuck does it actually do. This is what it does. So It's all about finding the position of the node in the octree. So neighbors are also identifiable by shifting the appropriate bits. Okay. So Morton coding, this kind of interleaving of the bits, allows you to more quickly get to the specific node that you want, but then also find the neighbors quicker. So I suppose that, right, like for example, this first digit here, 0, 0, 1, 1 here, right? So like just by checking this first digit, you immediately know that you're on this side here. And then just by checking the second digit, right, you immediately know that you're in this lower quadrant, right? Because all the ones here have 1. So I'd be curious to see how much that actually saved them in terms of memory. Maybe they do an ablation. 3 different data sets. Okay. 1, the replica data set. Okay, 18 different scenes captured by a camera rig. And the depth is actually synthetic. Okay. They have another one called ScanNet, which is 1,000 RGBD sequences and ground truth pose estimates. Okay, so I mean, these data sets are already a little sketchy, right? You have one where the depth isn't ground truth, it's synthetic, so it's made afterwards. You have another one called ScanNet, where the ground truth poses aren't actually ground truth, they're estimated. And then their last one is several indoor and outdoor that were captured with an iOS devices equipped with range sensors, right? So this is what we were talking about, where the iPhone, the latest iPhones have the depth sensors on them. Okay. Okay, different metrics for evaluation. Okay, they have mesh accuracy. Completion, which they're calling comp. Okay, and then they have like a kind of top 5 kind of situation, right? So in classification, sometimes you'll see what's called a top 5 accuracy, which is, hey, if you have 100 different classes that were possible for this classification model, sometimes it doesn't get it. It doesn't guess the right one, right? Sometimes it says it's a bus instead of a truck. But hey, if bus or if truck is in the top 5 guesses, right, then that kind of means something, right? Because it was almost there. So they're doing something similar here where they're saying, hey, if the reconstructed points are less than 5 centimeters away from the ground truth mesh, we're going to say that's fine. And then we're going to say what percent of the points are within 5 centimeters. The choice of 5 centimeters as opposed to 10 centimeters or 1 centimeter makes me think they literally were thinking about top 5 in their head. Okay, so formulation of chamfer distance, which is this mesh accuracy. Okay, so distance chamfer, point, and p minus q and squared, where p is 2 point sets sampled. Another metric they use, absolute trajectory error. This is you have the trajectory of your camera over time, and you have the absolute translational difference between the estimated and ground truth poses. But again, like the data sets they're using are estimated to begin with, right? So that's not even a actual ground truth. But okay. To illustrate our network architecture in Figure 5, our decoder is implemented as an MLP consisting of several fully connected layers and skip connections. The input to our network is a 16-dimensional feature embedding. The features are processed by 4 fully connected layers that each have 256 hidden units. The sign distance function head outputs a scalar sign distance function value s, right, the depth basically, and a 128-dimensional hidden vector. The color head has 2 fully connected layers with 256 units each, and we apply sigmoid to generate RGB values in the range of 0 to 1. Sample points, we use a step size ratio of 0.1 for sampling voxel points. And then they pick this voxel size of 0.2 meters. Let's actually go to that figure. This is their network architecture. So the embeddings that are coming here are the voxel embeddings, which represent kind of the position in space relative to other voxels, but also more information, right? There's kind of information there probably about the scene and about what's in that scene. They feed that through these 4 fully connected layers here. These have rectified linear units, ReLUs, right? Non-linearities, standard stuff. This last layer here does not, because you want to output the depth for the sign distance function, which can be negative, right? Signed. It can be negative or positive, so you don't want to put it through a ReLU. It also outputs, they also just take that feature vector that comes out of this first part, which is being given the gradients of the sign distance function. So the sign distance function loss is kind of propagating back through these. So these layers are going to get good at calculating that SDF. But then you also want the final color. So you're going to take the embeddings that you were giving to this kind of SDF part. You're going to concatenate them with the features that come out of that, and then you're going to feed it through another 2 fully connected layers here to get the RGB. And RGB, right, red, green, blue, each pixel, you're going to have a number between 0 and 1 if you're a float, and then eventually it'll be converted to 0 to 255 for actually rendering. But it's a float between 0 and 1, so they're going to put a sigmoid in between this FC here and this RGB in order to get it between 0 and 1. Cool. Maybe one thing about this paper that's kind of annoying is the figures are not put well. You know, it's like they're kind of like not in the right sections here. Let's read this section here, the reconstructions, and then we'll look at the figures. Test our system on reconstructing synthetic scenes using the replica dataset. IMAP, nice slam. Our method produces better maps. Then IMAP and performs our par with nice slam. Okay, so there's this kind of prior of densely populated surfaces in the two works that they're comparing here, so you'll sometimes get surfaces when there aren't. Okay, they say, we argue for real-world tasks, it is often more important to know where has been observed and where has not. So they're talking about kind of artifacts, trade-off between kind of filling in unnecessarily and leaving a bunch of empty spaces. The expressiveness of the signed distance representation. Okay, figure 6. So this is the ground truth. This is theirs. Again, the voxels they have are hard-coded to 0.2 meters. And then nice slam has a hard-coded length of basically the same size voxel. See how in the ground truth scene there's kind of legs underneath this table, and then there's also this flower pot here, and they're basically saying these thin structures are right, their system, the mesh that is reconstructed from that, right, the signed distance function that gives you the mesh. Theirs has the flower pots and the table legs, whereas nice slam does not. Okay, so they shit on the IMAP people here a little bit. They're basically saying that they weren't able to find the official implementation of IMAP because the original authors did not open source their code, so they basically stole, or didn't steal, but they used an implementation in a different paper. So it's not real IMAP is basically the answers. It's a copy, a probably not as good copy of it. And this is a general problem in machine learning that a lot of times when people benchmark and compare their algorithms to other existing algorithms, they might not use the original code for the existing algorithm, which is the one that has all the tuned hyperparameters, so they're basically using a not as good version of it. The reason people don't really care about it is because usually it ends up better for them, right? Because then their results are always better than the competitor results because the competitor results are not kind of implemented in the best possible light. No mesh culling. Okay. Okay, so these is original images, so frames of a sequence, which they took with their 13 Pro, iPhone 13 Pro, which has the depth sensors. And here you have kind of the mesh reconstructions, and I mean it looks choppy, but it's definitely there. You know, you have the cushions, you have the table, you have the foot of the table. You don't quite have the feet of the chairs here. This one's impressive just because this is such a visually busy scene, you know. Trajectory estimation results on the replica dataset. Again, you have the shitty implementation of IMAP, you have nice slam, and then you have theirs. You have the different metrics here. I like these. I love these. This just means lower is better. So this is the different scenes in replica. I guess the average is probably the one worth looking at. Right. The crappy implementation of IMAP is absolutely terrible. Nice slam is like an order of magnitude better on all of these metrics. And theirs is about half of what nice slam gets. But I mean, the numbers don't really mean anything because those metrics are kind of hard to really think about. You're better off looking at these pictures here and comparing. So here we have IMAP, nice slam, R's, and then ground truth. So okay, we have here, for example, bed. Our reconstruction results are much better than IMAP. It can be clearly seen. Okay, and then they put red boxes so you can really pay attention. So, for example, here, this box, they show that the wall quality, right? So in the replica data set, the wall is perfect. It's all perfect filled in square. In IMAP, right, it's really patchy, kind of crappy. Nice slam, you still have a little bit of those artifacts, little patchy holes. And then in theirs, you have the full flatness of the wall. Different details here. The TV, the back of the TV is really messy and nice slam. But in theirs, it just has the holes when it doesn't know what it's doing. Okay, and this is the top 5 accuracy thing. So percentage of points that are within 5 centimeters of the surface. Higher is better, right? 100% would be ideal. And these results are actually pretty good. These are all like some of these are high 90s compared to, for example, nice slam, where these are kind of in the 80s. Yeah, real scans are noisier and contain erroneous measurements, right? The ground truth is not there. Interesting. iOS can only provide depth maps with very low resolution. I don't actually have an iPhone, so I didn't know. But what is the depth map resolution of an iOS device? Ooh, 320 by 180. That's pretty crap. Okay, now we have a kind of section about time and memory efficiency. Since we make a local copy of the shared resources, right, the voxels features the networks, or the network, for the tracking process, each time the map is updated, the probability of resource contention between the two processes is low. Yeah, lock-free structure. So, right, you have this mapping process, and then you have the tracking process, and they're both using the same network, the same voxels, and the way that's going to be implemented in code, right? These objects in memory are going to have a lock associated with them. So when the map is updating, or when the mapping process updates the neural network that represents the nerf, the tracking can't use that, or can't get a handle to that object. So they're saying, yeah, there's more clever stuff you could do with lock-free structures where you don't have to kind of have these locks to make sure that things don't change at the same time. But it's good to know because it just means you can squeeze out more performance juice from this. Okay, they're doing this on a 3090. Why can't I, oh, offline. Seems like my internet died. Okay, are we back? Hello, 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 testing. All right, I think we're back. We might now be back. Ugh. Oh no. It's dying on us. Okay, it looks like paper pile's kind of dying on us, but... Oh, okay, finally we got it. We're good. We're good to go. Let's get to that last section. Let's read them, and then we can look at the code. Okay, RTX 3090. Tracking and mapping are profiled on a per iteration basis. Voxel manipulations have no significant impact. So 150 to 200 milliseconds to track a new frame, and 450 to 550 milliseconds for the joint frame and map optimization. So optimization is happening 2 times per second, and tracking is happening at 5 hertz. So this is very low. This is not 5 hertz tracking is not enough to play Beat Saber, right? Or mocap someone talking, right? But you know, this is more an algorithm novelty paper, so it's not really necessarily trying to like be extremely performant. Average time spent, volume rendering, back propagation. Yeah, kind of the most expensive part of this is the back prop. I wonder... Yeah, maybe they could mess with the precision of the data types used in this network. Maybe there's some trade-off there where they could use lower precision to do this faster. Yeah, this is huge. So because they have a sparse voxel grid, their embedding is much smaller. Did we lose all of our highlights? Wow, that sucks. Okay, applications. Okay, yeah, I mean, I wouldn't say this is specific to their application, but once you have a nice representation of a scene with right signed distance function, you kind of know where the surfaces are. You can put objects into these on these surfaces. You can have surfaces occlude virtual objects and so on. Okay, they have an AR demo, figure 9. Right, ground truth rendered image, and then they put this like couch, and you can see how like the corners of the couch and the chair occlude. The chair, which is real, occludes the couch. Our voxel-based method also makes scene editing much easier, since we can remove part of the scene by simply deleting its supporting voxels and associated feature embeddings. Explicit fast collision detection. Yeah, I really want someone to do like nerfs, but for physics, right? I think that the way physics is done in 3D games right now is just not great, and there's some clever way to basically use neural, and not rendering, but in this case neural object representations, maybe with voxels too, to make it more efficient, where I think you could capture the interaction between two objects more richly with a neural net than you could by just having a collision mesh and then having two collision meshes, and then based on how much they intersect, you know, and then just like using physics equations for that. Yeah, I think this is one of the bigger problems is like if you move one of the chairs in this system, it just kills it. Cool. So there we go. That's Vox-Fusion. Let's actually look at the code here. Installed script to build extra PyTorch modules. We can actually edit this and fix their typo. Roll typo. See what's in this install.sh. Third-party marching cubes, sparse octree, and sparse voxels. I mean, that's not even gonna work. Like, sparse octree and sparse voxels is not there. Open3D, matplotlib, pyaml. What is trime sh? Trimesh. Python library for loading and using triangular meshes. Pure Python. Uh-oh. 3.5 plus. Okay. We're good. 7 days ago. We're using triangular meshes with an emphasis on watertight surfaces. Okay, so you can make objects here. You can load STL files, GLB files. Oh, that's pretty cool. There's a bunch of little utilities here. Is it watertight, right? Or is there holes? The volume. The vertices. The center of mass. This is pretty good. I like this. Why have I never heard of this package before? This seems pretty badass. Huh. I like this. Who works on this? Oh shit, I know this guy. I also know this guy. This guy is a Carnegie Mellon guy. And this guy I know from, I think he did work on the picking challenge. Let's look at the insights here. Okay, we're seeing some activity. Okay, this is good. It's really mostly this guy. He's doing really the meat of the work there. He's continuing to push. Was really the first contributor and then kept going. This dude looks badass. Hidden activity. What is MDH? Oh, that's his name. Cool. So that's Vox-Fusion. See if we can see the video. Give these guys a like. Okay, and then where's their video? Where's the AR demo? They don't even have it. Oh. Okay, here you go. Placing new objects. There you go. Look at that treasure chest. Yeah, it really does. The occlusion is nice. Right, specifically there. Right, the chair occluding the treasure chest. That's a very good detail. Nice. Cool. This is Vox-Fusion. Thanks for listening, and see you guys some other day.